Okay, welcome back. So let's continue on our discussion on random variables and measurable functions. Okay, so last time we worked on some operations that preserve measurability. In particular, we showed the following. So if you look at the L0 space, which is the set of all measurable real-valued random variables, so let me write it this way in full. So omega f to r for Lr, okay, is an algebra, meaning that it is a linear space, a vector space, and a ring, meaning that you can do products of elements like x times y, and their operations are compatible with each other. Just like the compatibility of operations in the real line, like distributivity, etc., etc. So the relationship between addition and multiplication and scalar multiplication, etc., etc. So in other words, you can add real-valued random variables. You can multiply them. You can multiply them with numbers by scalars, and you again get real-valued random variables. You can also do it in the extended real case. But then all you have to do is to avoid the case infinity minus infinity. That was the only difference. So that's why the one with extended real line is not really a linear space, because the difference of two extended real-valued random variables is sometimes not well defined. Okay, so okay, that's what we showed. So today we will discuss limits of random variables. Okay, so here's some background. Let's say you have some numbers, not bar, x1, x2, in the extended real line, okay? Let's say you have a sequence of numbers. So you know what inf and sup are, I hope. So inf xk or xn, sup xn are always well defined in R bar. So infimum is what? It's not the minimum. Sometimes minimum doesn't exist. Therefore, it is the greatest lower bound that you can find. For instance, if you look at the interval 0 to 1, 0 excluded. So 0 is not an element of this interval, but you call it the infimum of this interval. And similarly, for supremum, it is the greatest lower bound. Okay? If you look at the maximum of 5 numbers, okay, it is always an upper bound on them. Did I say it in the wrong way? Least upper bound and greatest lower bound. So greatest lower bound is the infimum, and least upper bound is the supremum. Okay. Okay. So these are always well defined, and since these are always well defined, you can also talk about lim inf. Maybe first lim sup. So lim sup of xn as n tends to infinity. You define it in the following way. It is the inf of sups of the following form. So you look at the sup of the numbers after index n, and then you get a new sequence You can call it yn if you like. And now it is the infimum over all n. So since sup and inf are always well-defined, this is also well-defined. And there is also lim inf. So limit superior and limit inferior sometimes. So this is the sup of infs defined in the similar manner. Also always well-defined. And if the two are equal, so if the two are equal, we call it limit of xn as n tends to infinity, which can be a number in the extended real line. So, but in this case, we don't always say that the sequence is convergent. We only say the sequence is convergent. So in this case, we say further that the sequence xn is convergent if the limit is a real number. Okay. And we always have a comparison between inf sup, lim inf, and lim sup. Okay, so we have minus infinity less equal the inf is the smallest, then lim inf, then lim sup, then sup, and then plus infinity. And if the two lim inf, lim sup are equal, we call it just the limit. So if equal, so one important fact about convergence of numbers is that if you have a monotone increasing sequence, its limit always exists. Okay? So let's state it as a lemma and even check it, because it's one of the most fundamental facts about convergence that is used a lot in probability theory. So if x1 is less than x2, etc., then limit exists and it is equal to the sup. Okay. And for the proof, so we want to show that the limit is equal to the supremum. Okay? So if we can show that the lim inf is equal to the supremum, then lim inf is also equal to lim sup, and this means the limit exists, and also this is equal to the supremum. So let's look at the lim inf, which is the sup of infs. Right? So if you call it yn, what is yn? So you have x1 less than x2 less than x3. And what is y1? The minimum of x1, x2, x3, etc. So what is yn? xn, right? Exactly xn. This is our observation. Because the limit, the sequence is increasing. Therefore, the minimum of the values after some index is certainly the value at that index. Therefore, this is just the supremum of xn. So we're done. So according to this comparison, lim inf is equal to lim sup is equal to sup. So we're done. Lim inf, lim sup. So lim and sup. So of course, a similar result holds for decreasing sequences. So if you have monotone decreasing sequence, its limit always exists, and it is the infimum. And one more observation is that, let's look at lim_inf more carefully in general, okay, in the general setting. So what was lim_inf? It is sup of inf of xn or xk So if you call it yn, what is the property of this sequence? So y1 versus y2, which one is bigger? So y1 is the infimum of everything, whereas y2 is the infimum of x2 and so on. Therefore, you have better chance of getting a smaller number when you consider the infimum of everything versus infimum of 2 up to infinity, right? So if you look at this sequence, you also see monotonicity. Therefore, by lemma, the limit of the sequence exists, and it is equal to the supremum. So that's why we call this quantity sup_inf of these, that's why we call it lim_inf. This is the limit of the sequence yn, which is the inf of xk's. So that's why we say it lim_inf. Okay? And similar argument goes for lim_sup. So it's indeed the limit of the infs or limit of the sups, but at the beginning we define them as inf of sups and sup of infs. So this is just background to make sure that we're on the same page about convergence of real numbers and extended real numbers. Okay? Now, we'd like to work with the limits of random variables. So if we have on a probability space or on a measurable space first, if we have numerical random variables x1, x2, etc., we may define sup and inf and lim_inf and lim_sup in a point-wise manner. For instance, sup_xn is the function which is defined at every omega as the sup of xn omegas. That is what I mean by point-wise operations. Okay. Just like the way we added random variables, we multiplied random variables. This is how we take their inf, sup, etc. So the hope is that we have the same type of property. So when you take limit of those random variables, inf of those random variables, again, you get a random variable. In other words, these operations, these limiting operations, preserve measurability. So inf xn, sup xn, lim_inf, lim_sup, and of course lim, if exists, are all measurable if x1, x2 are measurable. Okay, so what do we need to show? We show that each of them is measurable. For instance, we can look at the event that the supremum of xn is less than some fixed value b and show that it is a measurable set, right? This was enough to show that a random variable is measurable. A numerical random variable is measurable. So and we will show, let's start with supremum, okay? This is an event in F. So what does that mean? Supremum of xn is less than b, less equal b. Supremum of a sequence is less than b. What does that mean? So if supremum is less than b, what can you say about x1, x2, x3? All of them are less than b. If x1, x2, etc., they are all less than b. If you have xn less than b for every n, what does that say? The supremum is also less than b, right? You can also tell this. So this is if and only if. You can just write it as intersection of xn less than b for all n. Now that xn is measurable, xn less than xn less than b is a measurable set, and therefore their countable intersection is also a measurable set. So we're done with supremum. Okay. So how about infimum? Well, if you have taken any course on optimization, so the relationship between minimization and maximization is very simple, right? You just do the opposite of what you're doing in minimization. In other words, you can write a maximization as a minus of minimization, right? So let's do it. Infimum of xn, you can see it as minus supremum of minus xn's. So you have numbers x1, x2, x3, etc. You're looking for the smallest of them. Here's what you do. You first take the negatives of them. So the relationship, the order between them is reversed. So now you should look for the maximum, the supremum of the minuses. But now the supremum is a number that is negative of one of those values here. So you should correct the sign by putting an additional minus sign in front. So now why did we do it? Because we would like to cheat from what we have just showed. Supremum is measurable. While xn is measurable, minus xn is measurable from last time. Sup is measurable, we just showed. And minus of measurable function is measurable from last time. Liminf is supinf. So now you can use the previous two facts. Infimum of a sequence is measurable. And supremum of another sequence of measurable functions is measurable. Therefore, the liminf is measurable. Limsup is similar. And limit is just the case where it exists, so is just the case where the two are equal. So if they are equal all the time, this means it is also measurable because it is lim inf and also the lim sum. Okay, so this is about infimum and supremum of random variables, infinitely many random variables, okay, a sequence of random variables. But not all the time we are interested in infinite sequences, but sometimes we are just interested in 3 or 4 random variables. So let's also say we can define the maximum and minimum of 2 numbers. For instance, the maximum of x and y, let me say x and y are extended reals. So this is the notation for maximum. Okay. If you like, you can see it as supremum of x, y, 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 etc. But this is, of course, not needed. And the minimum is denoted by this. So this is the minimum of x and y. And in particular, you can define the positive part of a number, which is the minimum of x and 0. Sorry, the maximum of x and 0. So if x is 5, 5 versus 0, 5 is bigger, so this is the positive part. If x is minus 5, well, x itself is negative, therefore 0 is bigger, and you get 0. So the positive part of a negative number is 0. And similarly, you can talk about the negative part of a number. So if x is minus 5, then minus x is 5. Maximum of 5 and 0 is 5. Therefore, you get the negative part of it. So the negative part of a real number is the absolute value. The negative part of a negative number is its absolute value. And the negative part of a positive number is just 0. Because if you look at the negative part of 5, for instance, minus 5 versus 0, 0 is bigger, you will get 0. So for every x, either x plus is 0 or x minus is 0, or both. If the number is just 0, it's both. And what is better is that x can be written as x plus minus x minus, because if it's a positive number, this part just disappears. Therefore, you have x equals x plus. If x is a negative number, then its positive part is 0, but its negative part is a positive number. Therefore, you have to make it negative by multiplying by minus 1. And further, the absolute value of x is the sum of its positive and negative parts. So this is all very nice, right? Therefore, we can apply these principles to random variables. Let me write it as a corollary to this proposition. So xy measurable and numerical random variables. Then maximum of x and y, minimum of x and y, x plus, x minus are all measurable, and even the absolute value are all measurable. Moreover, x is measurable if and only if x plus, x minus are measurable. So this second sentence is saying that if you have x is measurable, then for sure x plus is measurable because it is the maximum of x and 0. Okay? Similarly, x minus is measurable. And conversely, if you have x plus and x minus are measurable, but then x is just the difference of the two, therefore, if x plus and x minus are measurable, x is automatically measurable as the difference of the two things. And the nice thing about the positive and negative parts is that you never get a situation like infinity minus infinity, because every time you have one of them equal to 0. So you never have this situation. So any numerical extended real valued random variable can be decomposed in this way: x plus minus x plus minus x minus, and this is all fine. There is no ambiguity. And you can even add one more corollary. So let me list it as A, B, and C. So events like x equals y, x greater y, x less equal y, etc. are measurable if x, y are measurable. This you can also check as an exercise. So this is when we put in brackets, this doesn't mean that x of omega equals y of omega for every omega, but we're just looking at the set of omegas for which x of omega equals y of omega. So that's the event that this is happening. So now we are able to take limits, infimum, supremum, lim, inf, lim, sup. So, and I put special emphasis on convergence or limits of monotone sequences, increasing sequences, because our aim is to use building blocks of random variables, which are Bernoulli random variables and simple functions that we have seen last time. So our aim is to use them as building blocks of general numerical random variables. Okay? For instance, let's say we have an arbitrary positive measurable function, positive random variable. So our aim is now to prove that there exists a sequence of simple random variables, simple functions that are increasing like this, and then their limit is the arbitrary measurable function that we just fixed. So our aim is to use simple functions as building blocks of more general random variables. Okay? So here's an important theorem for this purpose. And we're going to prove it now. So let x omega to r bar plus, which is 0 to plus infinity included, be a measurable function. Then there exists random variables, or let me say simple positive functions, x1, x2, etc., such that x1 is less than x2 is less than x3, etc. And so if we have x1 is less than x2 is less than x3, etc., for sure the limit exists. What we are claiming is that the limit is also x itself. So our big picture is that, okay, we start with events, but events are in one-to-one relationship with Bernoulli random variables or indicator functions. Then we take linear combinations to get simple functions. So now we take one further step. This is the new step that we are taking now. So take limits to approximate arbitrary measurable functions. And we do it in the positive case for now, okay? Because it's going to be monotone. So let me say simple positive functions and arbitrary positive measurable functions, okay? So that's what we do in the theorem. Do you remember what a simple function is? So simple function is a random variable that just takes finitely many real values, okay? Just functions of the form 5 indicator A1 plus 3 indicator A2 plus 4 indicator A4, A3, etc., etc. So just finitely many values. You have finitely many events, and on each of the events, it takes certain values. So let's try to approximate an arbitrary positive measurable function using an increasing sequence of simple measurable functions, simple positive functions. So for each n, what we're going to do is to approximate the part of x, the values of x, only between 0 to n, and ignore the rest, okay? Approximate the values of x only between 0 to n, only in 0, n, and approximate the values in n to infinity by n. So if x is above n, just approximate it as n, namely ignore the values after n, but do some fine approximation between 0 and n. Okay? At step n plus 1, make your previous approximation in each interval 0, 1, 1, 2, etc., finer, and also approximate x for its values in n to n plus 1. So that will be the new part after step n. Let's make it more concrete. We'd like to define x1, okay? Here's what we're going to do. Okay? So first, we will ignore the values after 1. Ignore means it is above 1, so just approximate it as 1. Okay? Ignore the values above 1. So what are we going to do in the interval 0 to 1? Okay? We're going to make the following approximation. So if x is between 0 and 1/2, approximate it as 0 because you'd like to approach from below, okay? So this is x1 is the smallest. Increase it, x2, x3, etc. The largest will be x. Therefore, always find lower bounds. So on this interval, this is the lower bound. 1/2 to 1, this is what we approximated as. Now, how about x2? Again, we know if x is above 2, we approximate it as 2. Okay. There's going to be a part where we're going to refine our approximation for x1. So we're going to make a refinement here in the values between 0 and 1. And we're going to replicate what we did here for 1 to 2. Okay? So let's first refine this part. What do we mean by refinement? Well, you had 2 parts between 0 and 1. So now make it 4 parts. Halve every interval, okay? So that you have a finer approximation in this next round. So how are we going to do that? So halve this interval. 0, x, 1/4. 1/4, x, 1/2. 1/2, x, 3/4. 3/4, x, 1. And the approximations are now clear because we are in this interval. X takes values between 0 and 1/4. This is the approximation. We're approaching from below. 1/4, 1/2, 3/4. Okay? So at least for the values of x between 0 and 1, in this next round, we're getting a finer approximation. For instance, if x is equal to 1/4, if x is equal to 1/4, in x1 you would get 0. Now you get 1/4. It's increasing. Okay? So let's repeat what we did here. Repeat or cheat from what we did here. Okay? So now it starts from 1. And we increment by 1/4. So it is 5/4. 5/4 and 6/4, which is 3/2, 3/2, 7/4, and 7/4, 2. And the rest is done, was already done. So this is 1, this is 5/4, this is 2/3, and 7/4. That's a finer approximation. So that's the idea. So now we need to make it more general. Let xn be a fan of x, where a fan of little x. So for every realization of capital X, look at if you are in this interval. Okay? If you're there, your approximation is going to be this, the left endpoint. So this is happening when we are starting from 0. I mean, when we start from the value 0, in which case I is equal to 1. So I equals 1. You get 0 here, right? Up to what? Up to what? So from 0 to 1, you have 2 to n subintervals. But you have intervals from 0 to n. So from 0 to 1, you have 2 to n. 1 to 2, you have 2 to n. 2 to 3, you have 2 to n. Therefore, you have n times 2 to n intervals. For instance, let n be 2. 2 times 2 to 2 is 8. You have 1, 2, 3, 4, 5, 6, 7, 8 intervals. So we're not done. We have to add the following, n n to plus infinity of x. This is our function for each x between 0 and plus infinity. And we just apply it to x. So just to make it, again, concrete, for instance, x1 is what? x1 is 0 times the interval 0, 1/2 of x, 1/2 times indicator 1/2 to 1 of x, and 1 indicator 1 to plus infinity of x. Okay? This is what this formula is telling. So now we need to check what we claim. Okay? First of all, check f1 is less than f2, etc., etc., and the limit of fn of x is x for all x. That's a calculus exercise because these are functions on the real line. Okay? I'm going to skip it. But we know that fn of x is measurable as a composition of measurable functions. I should also say, check also that fn is measurable. But this is not really a big deal because fn is a simple function, right? It's a simple function. Just takes finitely many values. On each of those intervals, you have a certain value. Therefore, fn is for sure a measurable function from positive numbers to positive numbers. And so x is already measurable. This is given. Therefore, composition of fn and x, which gives us xn, is a measurable function. And finally, since f1 is smallest, f2 is bigger, f3 is bigger, and their limit is the identity function, since f1, f2, etc., converging to the identity function, which is fx equals x, okay? We have x1 is less than x2, etc., etc., and they converge to x, which is the identity function applied to x. So that's what we claimed. Of course, I'm not saying checking that these f1, f2, f3, etc. converges to the identity function is really trivial and just one line. I'm not saying this. So you can just sit down and check it. But I tried to give you the idea, okay? That's the concrete construction of the approximations. So between 0 and 1, so for the first time, here's your approximation, okay? So you do an approximation here and another approximation here, and the rest you don't care. So this is for f1. For f2, you make it finer over 0, 1, but you also include 1 to 2, and then you ignore the rest. How do you make it finer compared to f1? You divide, you halve every interval that appeared in f1. Okay, so. And you do the same here. And in f3, you're going to have even more intervals. So more in each interval and one additional big interval. Okay, so 0, 1, 2, 3, and you do it further. Eight intervals in each unit interval. So that's why we have n times 2 to n intervals, right? N times 2 to n in each. Okay, let's see the time. And I guess we can give a break.